In this video, we're going to explore the different types of representations that you can see in organic chemistry for molecules that you'll be drawing and naming. One way to represent chemicals in organic chemistry is by using a simple molecular formula. As you can see here, this is a molecular formula, C6H14. This just basically tells you how many of each atom there is in the compound. It doesn't really provide you any information about bonding or about structure. So it's useful in the sense that you know what's in it, but not so useful because you don't know how things are connected to each other. And also, as you'll learn later on, many molecules might have the same chemical makeup. They might have the same amount of carbons and hydrogens, but they can be connected in different ways, so they're not going to be the same at the end. So this provides you just a very basic information you need to know. For more detailed information, there's other representations you can use. You can use what's called an expanded or Kekulé formula, and that's where you show how everything is bonded. So you show each carbon bonded to each hydrogen or other molecule that's involved as well, and you show each of the bonds that are present. That's different from a structural formula that is condensed, in that you'll notice the condensed ones does not show every single bond. It shows where you have a branch coming up, but everything else is condensed. All the other bonds are removed, so you don't see the lines between the H and the C, and you don't typically see the lines between the C and the C. In some cases you can. This is also considered condensed, but this is as condensed as you get over here. And you can even get more condensed than that, as you can see in this example here. So typically, you'll see that when you want a lot of information in detail, you'll go with an expanded structural formula. And if you just want to do something quick where you want to get the general idea of how things are bonded, you can do a condensed structural formula. And then lastly, the fastest drawing is the bond line or skeletal diagram, where all the carbons are represented by points on these lines here. So these all represent carbons, and you don't show any of the hydrogens. They're just implied. So, for example, this carbon here must have 3 hydrogens, 1, 2, and 3. And then the reason I say 3 is because the other bond that it makes is with the other carbon over here. And remember, each carbon has to take 4 bonds or lines. This carbon here would have 2 implied hydrogens because the other bonds are to these carbons next to it. So you can also represent these as bond line or skeletal diagrams. Any other atom that's not an H or a C will be shown in these. So for example, if you have an O, an N, an F, a Cl, an I, you do need to show them. That includes groups like this, like hydroxide, or your NH group, your amine group, and other halogens. They do have to be represented in there. You can't say they're implied. So you'll notice here we have some practice problems that you can attempt where you have to convert from one form to another. Here we have a condensed structural diagram. And what we're going to do is we're going to convert it into a bond line structure. You'll notice there are 3 carbons. So we simply start with our first point, count, that's carbon number 1, carbon number 2, carbon number 3. And there we have our bond line structure. These represent the same thing overall. These would both have the same formula. There's 3 carbons, and for H's you have 3 plus 2 plus 3, 8, C3H8. Here we have the bond line structure, and we want to convert it to a condensed formula. So we'll just start at one end of the molecule. Let's start over here. This must be a CH3. For the carbon to have all its bonds, it's connected to 3 hydrogens, and then connected to this carbon over here. And for the carbon to have all its bonds, since it's connected to 2 carbons already, this must be CH2. And then the next one over here is CH2 as well. And then this one over here is going to be CH3 for the carbon to have its 4 bonds. General rule is that if you only have carbons and nothing else connected to it, typically the ones at the end are going to be CH3, and the ones in the middle are going to be CH2, unless there's other things connected to them or there's double bonds or triple bonds. Let's try this next one over here. So this is a molecule with three carbons. We have the bond line structure, and we have a double bond O on one of the carbons. So this first carbon is going to be CH3. And the second carbon, it can't be CH2 anymore because we have a bond here, and two bonds there. So it's just going to be a regular carbon like that with a double bonded O like this. And then our last carbon there at the end has a bond to this one. So that means there must be three H's connected to it. If you want to draw, I'll just show you an example. If you want to do an expanded formula of this, you would do, so the C, H, 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 C, double bond O, C, H, H, H. Here we have a cyclical compound, and we want to make a line diagram for it. So basically, we're just replacing each of these points here by, well, points on a triangle. So we have three carbons. There we have our cyclopropane. And lastly, here we have benzene. So you'll take a look at benzene over here. It has some double bonds in there and some single bonds alternating. Another way to represent benzene is like this, because if you'll remember that this is actually, these double bonds can alternate their position, or we can draw it in different ways, we should say, and those are all resonance structures. So we can often represent it by this circle to represent all the resonance structure that contribute to benzene. We'll learn more about that later on. But right now, let's go ahead and deal with one carbon at a time. So we'll start with this one. That carbon must have, since it already has three lines connected to it from each carbon here, 1, 2, 3, only one H. So this is our first carbon, double bond over here. This carbon also only one H because it has double bond, line, so just CH. And then this carbon here, also just, this carbon there, also just CH. This carbon here, also CH. This carbon here, also CH. This carbon here, also CH. Don't forget to make your double bonds. And then we can connect there. And you can go back at the end and take a look to make sure each carbon has 4 bonds. So for example, this is 1, 2, 3, 4 bonds for this carbon. For this one here, we have 1, 2, 3, 4 bonds for this carbon. For this one, 1, 2, 3, 4 bonds for that carbon. 1, 2, 3, 4 bonds. 1, 2, 3, 4 bonds. And then 1, 2, 3, 4 bonds for the carbon. So that would be the condensed structural formula for benzene. And so in this next part of the lesson, you're given some examples of molecules in different formats, and you have to convert from one format to another. The answer keys can be found here, but we'll take a few up together in this video. So we have the expanded formula over here, and we want to write the condensed one. So we'll start with this carbon over here. This would be CH3. Next, we'll go to this carbon, and we have to make the line connected here. There's one H connected to it, and then that's getting bonded to a CH3 above there. Then we'll go to the next carbon, which also all these carbons here, there's 3 of them that are CH2s. And then lastly, we have the Br. You can further condense this. Some people will put this part here, for example, in a bracket and put it next to this. Some people will join all these together and say there's 3 of them. So there's other ways to further condense the molecule. We're going to stick with condensing to about this amount here. And then we can do our line diagram here. So we have how many carbons? 1, 2, 3, 4, 5. 5 carbons. There's no double bond, so we're just going to make the 5 points. So there's 1, 2, 3, 4, 5. On this carbon over here, there's 1 carbon, so a line that goes up here. It could have pointed down as well. That would have worked just fine. And then on the end, we have a Br. And that is our bond line diagram. We can do the same example over here, or a different example here. So we have the expanded structure. Let's do a condensed structure. So Starting from the left side, we have three H's on there, then two CH2s, for this one here, you could just do this if you wanted to, or you could have done this. I'd be good with either because we need to focus on these groups eventually, and I want you to know that this means the same thing. So C double bond O, OH, COOH. And then a bond line diagram. Let's see, we have 1, 2, 3, 4 carbons. So 1, 2, 3, 4. And then we have to do our double bond over here, and then our OH over here. And there's our bond line diagram. Let's try the next example here. So we'll do condensed first, starting from the left side. We have CH3, then a CH, then connected to that going to the top, we have a CH3 over here. Now over here we have a CH connected with a double bond, then another CH, and then a CH3. Now, if I gave you this structure like this without the lines in there, when it's in brackets like that, it typically means that it's on the carbon to the left as a branch. If I gave you this, you would need to know that there's actually a double bond in there. And the way you would know that is you'd say, well, let's count what there is in the carbons. This carbon over here is connected to a carbon this way, so that's one bond. Connected to an H, that's another bond. And connected to a C, that's another bond. There'd be a bond missing. So you know that there must be a double bond in between those two carbons to account for that. So sometimes you have to count and think about how many things or atoms are bonded to your carbon. Let's do this as a line diagram now. So we have 1, 2, 3, 4, 5 carbons, and we do have to represent the double bond as well. So we have 1, 2, 3, 4, 5. And the double bond is on, so this is 1, 2, 3 on the third carbon. So 1, 2, 3, and the fourth. Now, I didn't count properly there. I should have actually counted from the right side, and you'll learn more about that later on. So it's actually on the second carbon. So this would be 1, then 2. But again, more details than that to come. And don't forget your branch, which is a one line there. And there is our bond line skeletal diagram for that situation. Here we have convert the line formula into an expanded formula, or vice versa. And then you can check your work. So I would try these out without watching the video, and then afterwards come and check your work. So here we have a bond line diagram. We want to convert that to an expanded formula. We have 1, 2, 3, 4, 5 carbons. So I'm just going to connect 5 carbons first. I'll make my parent chain. That's 3, 4, 5. And then basically the ends, I need to have 3 H's on all of them, and the rest is basically 2. So there's my H's. Notice I'm just completing these to get the 4 bonds on each carbon. The more practice you do, the quicker you'll get. Okay, here we have an expanded structure. We need to make it a line diagram. So we have 3 carbons. So 1, 2, 3. Double bond over here. That's it. Don't have to show the H's. This one looks a bit messy. Let's outline where our carbons are. So we have a carbon here, 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 and here. I know that based on where the H's are attached. So I'll start off by drawing from here, and I'll make my way all the way down to here, and then I'll add a branch after. So there's 1, 2, 3, 4, 5 carbons. So 1, 2, 3, 4, 5 carbons in that main region I just drew. I'll on the third one here, so this is 1, 2 on the second one. So we're in a second one, so 1, 2. There's another line. I can make a point down or up. It doesn't really matter because the molecule moves around. On this carbon over here, which is right here, we have a double bond. Oh, like that. And that represents the line diagram for this messy looking compound over here. One more thing to mention is that in these structures, these expanded formula structures, you don't always have to show the lone pairs. So if they're not represented, just do remember they are there. So there are 2 lone pairs on there. It's not that they're gone, and there's an exception. It's just that sometimes in these diagrams, you don't have to represent the lone pairs, but they are still there. So make sure you go through this video before proceeding to other problems. You should know how to represent molecules in any form that is asked. If I give you any of these forms, you should know how to name the molecule based on that and understand what the bonding means and what the structure implies based on the form provided.